So previous class I end here for discussion of the mirage, okay, and the concept of the total internal reflection. And here I discuss how the image is inverted by 90 degree and 180 degree. Okay, so here we choose for previous class actually end here discuss mirage. So I choose a prism here. Suppose we choose a prism. Okay, and now the object is stand here. Someone the object now top part, there's a incident ray fall on the surface, and you see that the surface and make incident make angle 90 degree. So the normal and incident ray are overlapping. So that's why in refraction there is a no bending. In refraction there is a no bending, so they follow the straight path. After falling on this surface, this interface, and you see that very carefully, there is a total internal reflection, and here is total internal reflection. Now back to the same medium, and consider that is a optical density inside. Suppose density suppose 2 and outside density 1, and outside is less dense than inside. Inside is more optical denser. And you see that the same condition is like here, perpendicular, these are the incident ray perpendicular this interface, there is no bending here, and you see that portion object head fall on that surface interface. Now object head, and here is the object head. Now the leg interface and the leg image is 90 degree inverted. So here the object, and see the very carefully, image is 90 degree inverted. Okay, and now we draw another diagram when I create an image is 180 degree inverted. So now we choose a prism. Okay, same condition here, inside a dense 2 and that is outside. Inside is more denser surface, that's medium than outside, because there is actually density means the optical density. Okay, so now this is called suppose incident ray from object. Okay, suppose the object here head leg. Okay, so fall on this surface, so there is no bending. Okay, this is a straight path. Okay, don't be confused, this is a straight path. And now the total internal reflection, here also total internal reflection, and that is a perpendicular, so that side there is a refracted ray, no bending here, because the incident ray perpendicular to the interface. And see that here there is a top part, head, and head. Now the head, leg, and leg. And you see that very carefully, the image is 180 degree inverted, and here the image is 180 degree inverted. Okay, so that's why these are with help of two diagram we convert the images inverted image gate without changing the size of the object. Okay, and for we use another diagram, so use a trapezium, same condition, trapezium here. So if there is an object here, there is a ray fall on this surface, incident ray, there is a normal refraction, and here you see that there is no total internal reflection, so there is a normal refraction, that's why there is a bending. Similar condition here, the inside is 2 and outside density is 1, so outside is less dense than inside is more optical density, so that's why there is some bending here. So it is a normal, so there is some bend towards the normal. Suppose for here, similar condition here, bend towards the normal, and here the total internal reflection. Now that back, and here the back. Here these interface make total internal reflection, and the back to the same medium, and here is a now denser to rarer normal refraction. Now there is a bend away from normal, and there's that there's a head, this line ray head and head. This is the head, leg, leg. There is a leg. And you see that image is 180-degree inverted. Here also use a trapezium type of prism. So create a image also 180-degree inverted. Okay. Now clear the concept. And we use another important concept that today's communication is the optical fiber. An optical fiber operation based on total internal reflection. Okay. So we discuss optical fiber, okay, and that is the optical fiber. Today is the modern communication, that is the optical fiber. Okay, that is the optical fiber. These are the, and these are based on operation based on total internal reflection. Suppose there is an incident ray. Here the incident ray fall on greater than critical angle. So if a incident ray means data are optically, okay, optically coded. Yeah, that's the data are optically coded. Okay. So incident ray fall on greater than critical angle. So there is total internal reflection. So back to same medium, same greater than critical angle, same. And you see that very carefully. There is a no loss. There is a zero loss. There is zero loss. If a incident ray, if I same amount fall here, receiver gets same data. So receiver gets zero loss. The perfect communication, okay, perfect channel actually. These are the perfect channel. That channel makes zero loss. And here that refractive index, very important. Refractive index, okay, there's an n. Suppose that here outside that is a low, and inside that is n, refractive index is high. So that means high density here. That means inside optical fiber density 2 and density 1, density 2 is much greater than density 1, because we know that in case of total internal reflection, the light obviously travel from higher density to lower density medium. Okay, density towards lower density medium. Okay, clear. Now the outside means there is some jacket or coated here. I actually ignore that, but how to manufacture that optical fiber? Outside means there is some coated here to protection actually, and this layer is called cladding layer. So ignore that part, that is not in our syllabus. That's why I ignore that part. Okay. We discuss another important concept, that is a refraction of a spherical surface. Okay, and here we discuss the refraction at a spherical surface at any length, and any length we discuss refraction of spherical surface and any length. Okay, so first we choose that a convex lens. Okay, so first we choose that a convex lens, convex, and one side of the convex lens, obviously. The diagram now, next page, the diagram is look like this. Okay, and these are the high density medium. This is a high density medium. Okay, suppose that looks like this, and that's the principal axis. Okay, and there is an object here. Here is object O, and object from object to that surface called incident ray. Okay, and now draw a normal here, and now normal is now look like this. Okay, see, normal is not look like this. Okay, and normal passes through the C, center of curvature. Draw normal here, and that's the obvious, that's the incident angle I, and you see that there's a bending. So light travel from rarer medium to denser medium. So suppose these are the more optical dense medium. So that's why bend towards the normal. So look, create an image here. There is an object, there is an image. So here this distance is called U, object distance, and this is the radius of curvature R, and this distance is V from pole to that image. Okay, and suppose this name I say that is called M. Okay. And here you draw a perpendicular from N and ignore that distance, that is very small compared than other length. Okay, R, U, V. Okay, it's very small, that's why I ignore that part, and this point be the N here. This point be N. Sorry, this point be the M here. Alright. Okay. Now let's see their diagram and calculation here. So now if I compress the diagram, better understanding. Now we see that the triangle. The first triangle is NOM triangle, and tan of angle NOM, because the NOM is right angle triangle, that is equal to perpendicular NM by base. Base is the OM, and another triangle tan NMC triangle, NMC, tan of this angle, so that is tan of NCM, that is a perpendicular same NM by, these are the base, by MC. Now the another triangle NMI, similar tan this angle, tan NIM, perpendicular same NM, here the NM by base from MI. Okay, and he gets a 3 equation, 1, 2, and that is the equation number 3. 3 equation you get. Okay, and now see that is I incident angle, and that is R, that is a refracted angle. This R is a refracted angle. Okay, and now here see the triangle see the triangle NOC, triangle NOC. I is the exterior angle, that is equal to know that sum of two opposite interior angle, that is this angle plus this angle, because NOC triangle, that is exterior. If I extend this, okay, so I equal to this angle NOM plus NCM, exterior angle equal to sum of two interior angle. If I actually CN is extended, that's the interior exterior angle be the I, and there sum of two interior angle. And you see that for small angle approximation and tan this angle, suppose they call tan theta, and this angle tan theta with this theta. So small angle approximation tan theta approx equal to theta, and it's called small angle approximation. Okay, so NOM, that is equal to NM by OM NCM, that is equal to NM by MC. Okay, that's the equation number 4. And now we check what is the value of R. Now see that there's angle R. Now draw here. Some draw means there is a draw parallel. Draw a parallel from N parallel to that principal axis. Draw parallel to principal axis from N on left side. Parallel. And see that this angle and this angle will be the same because these two are alternate angle. And same condition here. This angle and this angle be the this angle and this angle be the same. Okay, because similar they are alternate angle because okay. Now we see that here, so from R, that is angle R, and we get if I minus this angle minus this angle, that this angle means NCM minus, and this angle means this angle, that is NIM, we get R. So NCM minus NIM, for R equal to, we get right here NCM minus NIM, and NCM, that is equal to NM by MC, NM by MC, and NIM means NM by MI. That is equation number 5. And from Snell's law, now from law, okay, that is sin I by sin R, okay, sin I by sin R, that is equal to N21, that is N2 by N1. And now cross multiply N1 sin I, that is N2 sin R. And now in that equation, equation number 6, we put equation number 4 and 5, I and R value put in 6. So I and R put in 6, means 4 and equation 5 put in 6. So N1, and for small angular approximation means N1 sin I, obviously, okay. So sin I means I. So sin I approx, that is I, sin R approx R, for small angle approximation. Now N1 sin I means we get Nm by Om, Nm by Om, and Nm by Mc plus Nm by Mc, and N2 sin R, Nm by Mc minus Nm by Mi. And you see that Om actually, that Mn common in all sides, Nm, so ignore that. And final answer I get N1 by Om plus N1 by Mc, N2 by Mc minus N2 by Mi. Okay, and here we see that, now see that N2 by Mi from this side left to right plus N1 by Om, and this jump to right side, N2 by Mc minus N1 by Mc, and here N2 by Mi. So Mi means, you see that Mi means V, actually these are the M, okay, this point with the M. So that means V plus N1 by OM. So OM means U. OM means U. N1 by U. 1 by MC common, that is N2 minus N1. So what is the value of 1 by MC? So MC means M2C, that is R. So final expression I get N2 by V, N1 by U, N2 minus N1 times 1 by R. That's the final expression. Okay, that's the equation number 7. And these equation hold for both concave and convex lens also. Okay, both lenses are satisfied. Now here we discuss with the help of this equation we derive a lens maker formula. Okay, and that is a refraction by a lens, same condition refraction by a lens, and we choose here that is a obviously there is a lens. Okay, actually you choose mainly a surface. Okay, you choose mainly a surface of the one surface of the lens. Okay, that's why these are called convex lens, one surface of lens. Now we choose both surface of lens, means that's now principal axis, and here that object. Okay, fall on here, that is a eye image. Here the object, there is a bending. Okay, the convex lens, that's why these are bending. Okay, these are called convex. Okay, previous we choose a one left side surface, and here we choose left and right both surfaces. Okay, and the name is called, suppose that is a N1, there's a N2 refractive index here, and that is O, B, that's a D, that's a I. Okay, and that is a U, object distance, that is a B, image distance. Okay, and here that surface is A, that is a B, C surface, ABC surface, actually ABC interface, and here is a ADB interface, or we say the surface. Actually the geometrical image formation by the double convex lens. Geometrical image formation by double convex lens. The image formation of two steps, and here the image formation in two steps. First step is the ABC interface, ABC interface, and second step is ADC interface. When you choose the ABC interface, step 1, the ABC interface, now this look like this. These are the A, B, C interface, and here the principal axis, and here that is much denser. Okay, and here we see that the object, now the object here, object, that is a ray, that is obviously incident ray. Okay, and that incident ray, and here that is some tangent here, and draw normal. Normal passes to the C, center of curvature. Okay, these are the black line represent normal, and that is a refracted ray bent towards the normal. Here is created I1. Say that is a I1. Actually, inside that lens, what will happen? Actually, the inside the left side create a I1, and suppose I say that is a C1, and that is a B. Okay, and you see that is this angle B. It is a normal. This angle be I1, and that is R1 refracted angle. Okay, and here that radius of curvature, this length B to C, that is called R1. Say that. Okay, and that effective index, that is obviously that N1, and here is N2. Now the concept is, okay, and see that here this first step, the surface of ABC, interface of ABC, we apply the equation number 7, N2 by V and N1 by U. So N2 by V, so N2 by V means, suppose we apply here, N2 by BI1. Here we see that there is an image BI1, that is V, BI1 plus N1, that is OB, that is U, object. Here is a object U, and here is a B, U, OB, and here we get N2 minus N1, that is by R1. R means BC1, BC1. That's the first left surface, ABC surface. Now we jump to the right surface. Here we actually apply equation number 7. Don't be confused. Okay, number 7 here we apply here 1 by R, and now that another surface, that is surface ADC surface, ADC, this surface. Now that's that dense medium here. Okay, and that's the principal axis, and here actually incident ray actually fall here. Here. Now back to the state, that is I1. So fall here actually. So okay, this ray denser to rarer medium actually. Denser to rarer medium, and here actually the normal, these are the normal, but normal means if I denser to rarer medium, then suppose the density, that is the N2, that's the N1. So denser to so the bend away from normal, there is a normal, away from normal means there is a normal, away from normal. Now this look like, these are the away from normal, these are normal, away from normal, and suppose it's called I. We say this is a I, and the surface is ADC, right side surface, ADC surface, and here this normal back their point is C, and it's called C2. Suppose there is C1, that's a C2, and this distance is called R2. Okay, and DI, that is a image here, create a image here V, and here object at DI1. Now this I1 treated as the object here. Okay, now that here important point. Now apply equation number 7, same as equation here, same apply here. Apply equation 7, Now to apply equation number 7, the equation first right here, N2 by V, N1 by U. 7 is N2 by V plus N1 by U, that is N2 minus N1 by R. Okay, these N2 that is now turned into N1 because there is now N1 and has a V. Okay, and there is a V is a image. Okay, and that is a image turned into DI. These are the image. Okay, that is N1 DI. And now similar N1 means now N2 and there is a U, and U is a DI1 and you see that there is a opposite. Okay, opposite side of that, that's why there is a minus. There is N2 and DI1 both are in opposite. If I say that Cartesian system, that is the left side here N2 and there is the right side, that's a minus here. And now here that is a minus. So N1 minus N2 change here, and R that is a DC2 in left side. Also origin is there's a left minus x, that is a N1 minus N2 DC2. And if I change the sign here in, so obviously there is a minus because the left side DC2 sign convention, N2 minus N1 by DC2. Okay, that's very important. That's the equation number 8 here. That's the equation number 8, and that is equation number 9. Okay, now if I added these two, equation number 8 plus equation number 9. So if I added these two, clear? Don't be confused here. Okay, first we write the equation number 7 here. Now compare these two, where the data is put here. Now put the data. Now I added these two, equation number 8 and 9. Now add 8 plus 9. If I added these two, first N2 by BI1, N1 by OB, N2 by BI1 plus N1 by OB, okay, plus N1 by DI minus N2 by DI1, that is equal to N2 minus N1 by BC1 N2 minus N1, that is DC2. Okay, and you see that very carefully, BI1 and DI1. So BI1 and DI1 be the same. Why? So BI1 and DI1 be the same because inside this length we ignore. Okay, so actually there is a length and I ignore inside this length. So there is a I and that is a BI1 and there is a DI1. If I ignore this length, so BI1 equal to DI1 if I ignore, and the very thin length, that is actually considered a thin length. So BI1 equal to DI1. So now these two the cancel and we get finally N1 by OB plus N1 by DI, that is equal to N2 minus N1 1 by BC1 plus 1 by DC, N1 by OB. And now consider if the object is an infinite, so object is an infinite. Say object is an infinite, so means here you see that object is an infinite. The parallel to that incident is parallel to principal axis, so object is an infinite. So if object is an infinite, so OB turn into infinite, and if OB turn into infinite, so the DI, now this DI turn into F and now DI turn into F, and you see that is final expression. One, that term is infinite, so 1 by infinite be the 0, so that term total be the 0, and final expression you get N1 by F, that is N2 minus N1 1 by BC1. BC1 means R1 and DC2 is the R2. So R1 plus 1 by R2. Now if 1 by F, that is equal to N2 minus N1 by N1, 1 by R1 plus 1 by R2. Next page, 1 by F, that is equal to N2 by N1 by N1 cancel with the 1 by R1 plus 1 by R2, and that is 1 by F, that is N21 minus 1 by R1 plus 1 by R2, and that is a lens maker's formula. That's very important, is a lens maker formula. Okay, that's a very important lens maker formula. Okay, and these are valid for both concave and convex lens, both are valid. Okay, and here this equation, and here in this equation, N1 by OB, if an object is not in infinite, here I will say that from derivation of lens maker formula I choose a condition apply here, but without the condition, that is N1 by OB plus N1 by DI, that is N2 minus N1, that is 1 by R1 plus 1 by R2. Okay, and you see that this expression N2 minus N1 1 by R1 plus 1 by R2, that is N1 by F. So you put here, that is equal to N1 by F, and here 1 by OB means that there is an object distance, and here you see that object are in left side, so that's why OB is minus. So object in left side, that's why OB is a minus U, and the image is right side, so DI, that is a plus V. So N1 by OB is a minus U, and N1 DI is a plus V, and N1 cancel, and we get 1 by minus U plus 1 by V, that is equal to 1 by F. So final expression I get 1 by F equal to 1 by V minus 1 by U. Okay, that's the thin lens formula. That is thin lens formula. Okay, that is a thin lens formula. Clear? The derivation of thin lens formula. Okay, actually today I take too much time, so that's why I end up class here. Next class I discuss some more about that convex lens and concave lens. Okay, so that's the today's end of class here. If you have any doubt for derivation, like how to derive the lens maker formula, what is thin lens formula, how to get that, if you have any doubt in geometry section, please ask in comment section, so I will try to give the answer. So today end the class here. Thank you.